Welcome to my YouTube channel. So today I'll discuss linear span. So let u1, u2 dot dot um are any vectors in a vector space B. Then we know that u1 u1 plus a2 u2 plus dot 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 plus am where ai are scalars is a linear combination of the vectors u1 u2 dot dot un. So the collection of all such linear combination denoted by span u1 u2 u3 or span uy is called linear span of this vector u1 u2 dot dot un. So this is the definition of linear span. So if there is m vectors in a vector space B. So we know this is a linear combination of all vectors where ai are scalars. Then the collection of all such linear combinations is called linear span of this vector. So it's denoted by span this or span uy. Okay. Now we discuss one theorem related linear span. So let S be a subset of a vector space B. Then span S is a subspace of B. Let this S is a subset of B. So linear span, this span S will be all such u1 u1 plus dot dot plus am such that all ai belongs to scalar that is field k. So this is linear span. So we have to prove that this is a subspace of B. Okay. So for that, first we know 0 can be written as u1 into 0 plus 0 into u1 plus 0 into u2 plus dot 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 plus 0 into um. So as 0 is a linear combination of u1 u2 dot dot um, so this implies that 0 vector belongs to this span S. Okay. And let us consider two element alpha and beta belong to this span S. Okay. So then alpha can be written as a1 u1 plus a2 u2 plus dot 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 plus am um, and beta can be written as b1 u1 b2 u2 plus dot 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 bm um. Okay. So as these belongs to span S, so alpha and beta can be written as a linear combination of the vectors u1 u2 dot dot um. So then alpha can be written in this form and beta can be written in this form. So to show this span S is a vector subspace of A, so we have to show alpha plus beta belongs to this span S, and also for any scalar k alpha belongs to this span S. So we prove these two, or in general, combining these two, we can prove A alpha plus B beta belongs to span S. Okay, so if you can show this, you can prove by showing this. So now we show this. So as alpha and beta is this, so alpha plus beta can be written as a1 plus b1 u1 plus a2 plus b2 into u2 plus dot 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 this vectors u1 to um. So therefore this implies that alpha plus beta belongs to span S. Okay, so we assume that alpha beta belong to span S and we prove that alpha plus beta belong to span S. And also k into alpha, that is k into u1 dot 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 am can be written as k into a1 u1 dot 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 k into am so this also a scalar, this also a scalar. So k alpha is also a linear combination of the vectors u1 u2 dot dot so from this we can conclude that k into alpha belongs to span S. So we assume that alpha and beta belongs to span S, and is any scalar small k belongs to capital K. Therefore we prove alpha plus beta belongs to span S and k alpha belongs to this. So from this we can conclude that this span S, where S was the subset of a vector space B, that is S contains u1 u2 dot dot um. So this is a subspace of the vector space K. So this is very important theorem for your upcoming exam. Now we discuss row space. So for that, let A be a m by n matrix over the field K. So you can take K as set of A numbers. Okay. So this has m row n column. So m row, if we, so A has m rows R1, R2, Rm. So R1 can be written as A11, 12, 13, dot 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 A1n. Similarly, R2 can be written as A21, 22, 23, dot dot A2n. So similarly, Rm, A, M1, M2, M3, dot dot AMN. Okay, these are rows. So these as a n tuple. So this belongs to this Kn, that is nothing but Rn. So this belongs to Kn, this belongs to Kn. Okay. So this row of this matrix A can be viewed as a vectors of this vector space Kn. If K is a field, then we know Kn is a vector space. So this row of this matrix can be viewed as a vectors, as this is n tuples, so it is a vector in Kn. Okay. So as this is a vector, so if we take this R1 to Rm, as we discussed U1 into Um, so R1 R2 dot dot Rm, these vectors span a subspace of vector space Kn. Okay. So these vectors will span a subspace of the vector space Kn. This subspace is called row space. Okay. So it can be denoted by row space of this matrix A as span R1, R2, dot dot Rn. So this is row space. So you can write row space. Row space of A is span of R1, R2, dot dot. So these are row of matrix A. So which will span a subspace of Kn, which is called row space. So we denoted by row space as this row space of A. So similarly, if we take column C1 dot dot Cn, so this has n columns. So Cn columns as a vectors. So it will row. So it will be vectors in Km. Okay. So as 1 2 dot dot m rows. So this each column contains m elements. So it will look like as, so let us take C1 will look like column. So A11, 21 dot dot A M1. So this column will same. Okay. And similarly C in nth column look like A1n 2n dot dot a mn. Okay. So this all will, so here m elements, so m tuple, so it will belong to km. So these vectors c1 c2 dot dot cn will span a subspace of km, which is called column space. Okay. Column space can be written as, denoted as column space of a is the span of C1, C2 dot dot Cn. Okay. So these are vectors in R. So this is a subspace of Km. So this is row space and column space. For today, that's it. I'll discuss more. So if you like it, please subscribe my channel and share with your friends. It will be very beneficial for your upcoming exam. Keep learning and keep watching. Thank you very much.